Welcome to the last plenary session for this afternoon. We have two eminent speakers that we're going to be introducing here shortly. One is the second Blight lecture, and then the second one would be the Proctor lecture. So with that, let me turn it over to David Toll.
Good afternoon, ladies and gentlemen. I'll just introduce the Blight lecture for you. So the Blight lecture is in honor of Professor Geoffrey Blight from South Africa at the University of Witwatersrand. He was a pioneer in unsaturated soil research, starting with his PhD at Imperial College London with Alan Bishop back in the 60s. So Geoff sadly passed away in 2013, but during his career he contributed greatly to no less than 4 technical committees of ISSMG on tailings dams, residual soils, and erosion of soils, and of course TC6, as it was, on unsaturated soils. He was an inspirational engineer and scholar, and TC 106 is very proud to honor him with a lecture in his name. The first Blight lecture was delivered at the International Conference on Unsaturated Soils in Sydney in 2014. And the first Blight lecturer was no less than Professor Antonio Jens, our Kevin Nash Gold Medal Award winner from this morning. But we're very thrilled that the second Blight lecture will be delivered here at the 19th International Conference of Soil Mechanics and Geotechnical Engineering. So thank you.
So our lecturer today is Del Freudlin. He's very well known for his excellent work in developing unsaturated soil mechanics. Received his degrees here as shown from Saskatchewan and from University of Alberta. We'd also like to point out that he has supervised some 65 master's and PhD students in his career. He is also an adjunct professor at Nanyang Technological Institute in Singapore and also an adjunct professor at Hong Kong University of Science and Technology, an adjunct professor at the University of Alberta. He's an honorary professor at University of British Columbia and a research professor at Arizona State. So he's quite busy. He's published over 500 journal and conference papers, and I could spend the next 20 minutes rattling off all his awards, but let me just mention, for instance, the Meyerhoff Award, the Terzaghi Lecture that's hosted annually by the American Society of Civil Engineers, and the Leggett Award from the Canadian Geotechnical Society. So with that, I'd like to invite Del to come up and give his Blight lecture.
Thank you, Mr. Chairman. Let me say also thank you to the organizing committee for asking me to deliver the second Blight lecture at this conference. I count it an honor to be able to do this. The title of my presentation today is The Role of the Soil-Water Characteristic Curve in Unsaturated Soil Mechanics. Unsaturated soil mechanics has enjoyed a rather rapid development during the past few decades. And it is mainly as a result of one particular relationship, and it's called the soil-water characteristic curve, or the water retention curve. We are fortunate that we have had friends in the soil physics area who did research on unsaturated soils for about 3 decades before we ever got started. And so we have a lot to learn from them and a lot that we can glean from them. And today I will summarize some of the key findings of their research that were very relevant to our work in geotechnical engineering. I will also summarize very briefly some of the developments that have taken place in geotechnical engineering. And I will talk about the concept or the estimation of unsaturated soil property functions. This originated in soil physics, but we'll see that we can take two tests, quite commonly run tests, one for the soil water characteristic curve and the other for the shrinkage curve. And we can bring those two tests together. We can interpret all of the volume mass relationships versus suction from those two tests. And then we can use it to calculate estimated unsaturated soil property functions. These are really the extension of our saturated properties into the unsaturated soils range. Once we have those functions, we can combine the unsaturated zone of a soil profile with the saturated zone. We have properties that will allow us to treat it as a continuum, both the saturated and unsaturated. And we can use that in numerical modeling, but I won't get into that part today. Let's start with a very important definition. The definition of the unsaturated soil zone. The United States Geological Survey defines it in a way that is very useful to us. It said it's that part of the earth between the land surface and the water table. If you study that statement, you realize that unsaturated soil zone is defined in terms of a stress state in the water phase. We will talk about it as soil suction. It is not defined in terms of a degree of saturation. That unsaturated zone can be subdivided into three main types: the capillary zone, the two-phase zone, and the dry zone. Let me put it on a picture. And at the bottom of this slide is the phreatic surface, the water table. Immediately above that is a capillary zone, where the water phase is continuous, but the air phase is not. Above that is the two-phase zone, where the air phase is continuous and the water phase is continuous. And above that, if the zone is large enough, we could have a dry zone. I draw on here an equilibrium condition. If there is zero flux across the ground surface, this will be the state of stress in the water phase, regardless of whether the soil is a sand, a silt, or a clay. It is an important equilibrium condition for us to start with. Now, over at the right-hand side of the slide, I would like to plot the degree of saturation of the soil versus depth. It is close to 100% through the capillary zone. And then there's a break in this relationship. And if we follow it far enough, there will be a second break. These two breaks, one the air entry value of the soil, and the other the residual break, will become the most important characteristics for us to define in order to do the analysis that I will present. Now, this relationship on the right here looks like a soil water characteristic curve turned on its side. Well, the world is not quite as simple as I just showed you, because the ground surface always has a moisture flux. If water is not going up to the sky in terms of evaporation or evapotranspiration, water will be coming down. If water goes up in evaporation, this equilibrium line is drawn to the left, and the water pressures become more and more negative. When it rains, it comes back to the right, and the water pressures become smaller and smaller. So we have a trumpet shape up here that defines the changes in the stress state because our problem is driven by climate. Now, what are the pillars that we need to be able to put unsaturated soil mechanics into engineering practice? Well, we've had many conferences on unsaturated soil mechanics, and those conferences serve a very important purpose. They help us to develop theories, but those theories should go further than that. They should go to the point where they lead to proper, prudent engineering protocols that we can put into practice. Another very important pillar in unsaturated soil mechanics, in fact of all soil mechanics, because we are the people who take little soil samples, we test them in the lab, and then we do analysis on a real-world problem. But lab testing's always been important to us. But we have to change our thinking a bit. We have to move into a slightly different or significantly different paradigm. We go through a paradigm shift. We can't measure the real unsaturated soil properties. They are too costly to measure in the lab. So we measure something else. And that something else is the soil water characteristic curve. And we will use it to estimate the unsaturated soil properties. And we'll discover that our estimation techniques, if done correctly, appear to be adequate for geotechnical engineering practice. Of course, the other pillar is numerical modeling, the solving of nonlinear partial differential equations. And I won't get into that today, but the emphasis of my talk will be on the laboratory testing. I want to today describe the primary role that the soil water characteristic curve, gravimetric water content versus suction, plays in estimating our unsaturated soil properties. I want to also describe the secondary role that is played by the shrinkage curve in providing refinements to those estimations, very significant refinements. And I will illustrate how we can take the soil water characteristic curve and the shrinkage curve, and we can bring those two tests together, and they serve a very important purpose for implementing unsaturated soil mechanics into geotechnical engineering practice. Well, what are the requirements to practice unsaturated soil mechanics in geotechnical engineering? We still need our saturated soil properties, those constants that we have worked with. They are important. They become the hanger where we hang our unsaturated soil properties on. But the unsaturated properties will be extensions of the saturated property, and they will become mathematical functions. They will be functions of the stress state in the water phase. I will talk about how we can estimate those, especially for one particular problem, that of flow through water flow through soils. And I will explain how we can combine the soil water characteristic curve and the shrinkage curve. Another very important requirement for unsaturated soil mechanics is the fact that we need to quantify the flux boundary conditions for our problem. And it is a challenge, but I'm not going to talk about that today because we don't have time. And I won't talk about numerical modeling either. Let me give you a little summary of history of unsaturated soil mechanics. See, we go way back to the 1920s when our friends in soil physics were looking at the unsaturated zone and saying, we want to be sure to have enough water for plant growth. They were interested in water storage. And so they looked at water seepage through the unsaturated soil. They came up with the ways to estimate the properties they needed to solve this problem. It was about 3 decades later that in geotechnical engineering we say, well, you know, in classic soil mechanics, we don't only look at the water flow through the soil, we also look at shear strength problems and volume mass relations. And so the work done in the late 1950s was an extension of the work that the soil people in soil physics were mainly concerned with. Very significant research was done at Imperial College in London and under Bishop and his graduate students. And they produced graphs like this one shown here, where they plotted a ratio of the difference between the saturated shear strength and the unsaturated shear strength, and they plotted it as a function of the degree of saturation. Over time, we discovered that the degree of saturation could be measured relative to soil suction, and that relationship allowed us then to estimate the shear strength of unsaturated soils. Very significant work was also done at Imperial College on volume change. And I show a figure here from Blight 1961. It tells us, first of all, how complex volume change problems are. But there's other things it tells us as well. You'll notice on this graph he has separated out the effect of suction in the soil from total stress loading. You see, suction is always isotropic in its nature. Our net total stress, it could be one-dimensional, two-dimensional, three-dimensional, and its effect can be independent of suction. And therefore, our two-dimensional relationships became three-dimensional type plots for unsaturated soils. I want to move then now and ask, what did soil physics really give us? And I go to the summary given to us by Clute, where he summarizes this is the essence of the physics for flow through unsaturated soil. He points out that the relationship between degree of saturation and suction is not a unique relationship. There is an initial drying curve, and if you take it up to a very dry condition and you start to wet back, you don't follow the same path. It is hysteretic. And it'll entrap some air in the soil, and so when you try to dry it again, it follows another curve that he calls the main drying curve. And so this is the main loop that he defines as the bounding surfaces for the soil water characteristic curves. There's also other paths that could be followed, scanning curves, but the main curves are the drying and the wetting. Here's some of the statements he makes in his summary about the findings in soil physics. The soil water characteristic curve is a fundamental part of the characterization of hydraulic properties of a soil. And that is very important to the way in which we are going to use it in geotechnical engineering practice. He also said soil suction is an energy per unit volume, which reduces to a pressure. Very significant. Soil suction was defined in terms of matrix suction up to 1,500 kilopascals and total suction beyond 1,500 up to the limiting value of 1 million. That dividing line between low suction and high suction is rather arbitrary, but it's an interesting one. Where does it come from? It's a couple of things. First of all, the wilting point of a lot of plants is around 1,500. And so there's a division between the high and low suctions there. But it's mainly the ceramic disc that's used in our pressure plate devices. The finest pores that can readily be made in a kaolinite sintered ceramic disc is a 15-bar stone. And so we end up having this arbitrary division between matrix suction and total suction, but we will plot the data for both of these types of suctions on the same graph. He also pointed out that water content can be expressed in terms of weight, volume, or degree of saturation. This is important because we'll find that our friends in soil physics always used volumetric water content, and we use gravimetric, and it makes a difference. He also pointed out that the soil water characteristic curve was hysteretic, and of course it is not a unique relationship. That's what it truly is. So what are some of the concepts from soil physics that we want to retain? And then what are things that need to be modified for geotechnical engineering? Concept to retain. We want to retain the possibility of estimating unsaturated soil property functions. The whole concept of estimating those functions becomes very important to be able to have an applied science for unsaturated soils, one which does not cost more than what our clients can afford to pay. Secondly, we want to retain the idea that you will start your testing with a saturated specimen. It doesn't matter what the water content is in the field. When you sample that soil, you bring it in. They always wet the soil up to near saturation, started their test from that point. And it's going to be as a result of starting that test at that point that they're going to be able to truly define the air entry value and the residual value, the 2 points we need. What about if you're following a very different stress path in the field? The idea and the concept brought forth in soil physics was take care of all your stress path conditions in the analysis you perform, not the tests you perform in the lab. So what concepts need to be modified? We need to consider the importance of various volume mass variables. I told you they worked with volumetric water content. But you know, when you change the volume of a soil, that soil behaves differently than if you change the degree of saturation. And so there's a difference between the different definitions of volume and mass of water in the soil. We will also look at the importance of making use of the shrinkage curve and how it is most important to define the air entry value and your rate of desaturation for our soils. Now, there's many devices which have been proposed and been built to apply suction to a soil, measure the water contents, but it's become quite clear with time when you start to look at engineering firms that are putting unsaturated soil mechanics into practice, they rely very heavily upon a pressure plate device for the low suction range and equilibrium humidity conditions for the high suction range. And I will also say a word or two about measurement of the shrinkage curve and its importance. Here's a bank of about 13 pressure plate devices that we have going at one time. I think we have a total in our lab, commercial lab, about 30 devices. You'll notice that every device just has one specimen. This is different than what agriculture did, where they used to test many specimens at one time. And there's been a number of devices, such as this one built by GCTS, which looks like really a consolidometer for an unsaturated soil. The soil is put in a ring, placed on a higher air entry disc at the base. We can apply total stresses, and we can do K-naught loading. We can control total stress, vertical stress, and air-water pressure. We can measure water volume change, the diffused air volume, and total volume change. Now, let me emphasize that there's been a number of these types of devices that have been built in different countries around the world. Here's a set of 3 tests done on the device I just showed you on a silt soil. All 3 specimens were prepared the same. They were saturated up to this point. This is the initial drying curve. Then it was wet, and it came back here, and then they went dry. First of all, you notice that they're very reproducible. You notice that whether you'd use the main drying curve or the initial drying curve, you would get the same air entry value for the soil, one of the important characteristics we want to know. You'll notice that the drying curve is essentially parallel to the wetting curve, and they're just translated. They're congruent one to another. They're translated by a certain amount at their inflection point. In the high suction range, this little device has become very common in many laboratories. It's called the chilled mirror water potentiometer, built by Decagon. Now, so this red line divides the low suction range, where we plot matrix suctions, and the high suction range here. And here's a set of data that's sort of an average of some of tests that were done on Regina clay. This data becomes a thumbprint for that soil. It's the drying curve. We're going to do what we need to do with the drying curve, and then we're going to ask ourselves, how do we handle hysteresis? Well, this data gives us a thumbprint for that unsaturated soil behavior. But you don't want just a bunch of data points. You want to have an equation that goes through those data points. And so we come to that nasty-looking equation that we see over and over again in unsaturated soil mechanics, these sigmodal type equations that are semi-log, and they start out fairly flat, come down, have a bend in the curve, and then there's a second bend defined here, and they go to 1 million. Now, I fit this with the Fredlin-Zing equation because it goes all the way to 1 million. You put the data points into Excel spreadsheet, and you put in your equation, and you hit fit, and you get these 3 parameters. Now, I want to show you this equation. I'm sure you all came here to see this equation. It says gravimetric water content under any suction condition will be equal to the saturated value by all these factors that reduce it. Well, there are 3 fitting factors. They're the inflection point, the steepness of desaturation, and then a third fitting point. We don't need to worry about how bad this equation looks, because once you get it into your Excel spreadsheet, you get rid of it. Now, here is why did I say it's important to do a shrinkage curve in addition to a soil water characteristic curve? You see, we always measure gravimetric water content in the lab. But when we get those data points with gravimetric water content, we do not know whether the soil changed volume, changed void ratio, or whether the soil changed degree of saturation. And its permeability, its properties will be different for a change in volume than it will for a change in degree of saturation. I would point out that all the work ever done in soil physics made an assumption that there was no volume change as you change suction. Therefore, this term was equal to 0, and they said the change in water content would allow them to get the true air entry value. But we'll find out if there's volume change, they cannot do that. So what we need is when we have a sample soil we're going to test for the soil water characteristic curve, it might be about 70 millimeters in diameter and 1 inch high. We need to also take a small specimen and just allow it to dry for our shrinkage curve, about 3 centimeters in diameter and about 1 centimeter high. And we place it in a ring with no bottom. Just place it on a wax piece of paper and let it shrink. And as it does, it pulls away from the side. We measure the diameter and the thickness, and we measure its mass, and we get a series of data points that look like this. We plot void ratio versus water content. This is the shrinkage curve. And there's an equation for it, and it has the fitting parameters. And you can do that on your Excel spreadsheet as well. It says the void ratio is equal to the minimum void ratio, and another one which is the slope of the drying curve, which will be the same always, because we're starting at the same point. It varies just a little. And then this is the sharpness of that bending curve. So it's very easy to estimate the shrinkage curve, but you can also measure it very easily, with this being the most important parameter. To get this, you just have to allow a piece of soil to dry. So now we have 2 relationships, and we could look at this volume-mass relationship, and with the data we have collected, we can calculate a void ratio versus soil suction relationship, volumetric water content, degree of saturation, and we can calculate all our unsaturated soil property functions. And I'm going to use the seepage problems for illustration purposes. And I will illustrate the permeability function, which can be a function of void ratio change and degree of saturation change, and we can plot it versus suction, and it's called the permeability function. Water storage function will be the slope of the volumetric water content always versus suction. So why is it so important to have these 2 tests? I want you to look at the bottom of the slide. We have a partial differential equation here which describes flow through a saturated soil or an unsaturated soil. We're solving for head, H, but there's a permeability value, and it is a function of degree of saturation and void ratio. There's a water storage variable. So these are the soil properties, and this one is a function of volumetric water content. Well, if I go into the lab and measure gravimetric water content versus suction, and also get the shrinkage curve, I can calculate the degree of saturation, soil water characteristic curve, the void ratio, and the volumetric water content. So this is why we need these two tests if the soil changes volume. That same data I just showed you, so we can separate out the void ratio change. And you can see that that soil underwent about 20% volume change before it no longer changed volume as it dried out to 1 million kilopascals. I can calculate volumetric water content because I have the gravimetric water content, soil water characteristic curve, and I have the shrinkage curve. So I can calculate this, and it'll look like this. And when I want to calculate its slope, because that's water storage, this is what it will look like. So I take that curve I just showed you, and I differentiate it. I get the slope of it. And I have the water storage. I can also, with those same two functions, I can calculate degree of saturation. Specific gravity times the soil water characteristic curve divided by the shrinkage curve gives me that. So if I look at that, now this curve comes out and it'll be quite distinct and it'll start to desaturate. And this is the degree of saturation plot. And if you would have noticed before, the gravimetric one started to bend about an order of magnitude sooner. Here we would estimate the air entry value around 100. It's almost an order of magnitude different than what we would have gotten from the gravimetric water content curve. Now we can, with this degree of saturation, I can convert this to an arithmetic scale. I can differentiate it, the equation, get the steepest slope, extend it back, and I have a fixed equation to give me the air entry value coming to 147 kilopascals. Now, to get the permeability function, we need to integrate along the degree of saturation. So we do integration from the air entry value to high suctions, and we get the permeability function. So if I'm showing for the case of no volume change, it comes out, and at 147 kilopascals, it starts to desaturate. And this is what the permeability function would look like. Now, how do we handle hysteresis? Let me just make a comment about hysteresis before I conclude my talk. We looked at the drying curve. Sorry, I got to go backwards there. A drying curve here. At the inflection point on the drying curve, it was 262. At the inflection point on the wetting curve is 117. If we assume that these curves are congruent, they're parallel to one another, the only variable that changes is that A variable in the equation. We estimate hysteresis in terms of a percentage of a log cycle. Sands may vary 25 to 50% of a log cycle. Clays and silts and clays might be more like at least an order of magnitude. We can integrate along the wetting curve as well, and now we get a permeability function for the drying curve and the wetting curve. It is more important to do a proper interpretation of the data and get the right air entry value points than it is to even have an accurate value of the hysteresis loop. Let me say it another way. The hysteresis loop on the permeability function will be less than what the error would be if you did not take volume change into account. So that shrinkage curve becomes very important to us. So just in summary, to go back again, we needed a soil water characteristic curve measured in terms of gravimetric water content. We combined it with a shrinkage curve, and that allowed us to calculate degree of saturation, void ratio, and volumetric water content, soil water characteristic curves. We differentiate this, we integrate along this, and we get our functions for our soil properties. I've used this example of flow through an unsaturated soil to illustrate how we can go into the lab, measure make two fairly easy measurements and get the information we need to estimate our permeability functions. Now, there's a lot of, I've used this word a lot today, estimate. But I want to, first of all, say that if you don't rely on an estimated procedure, it's going to be far worse. With no estimation procedures, we can't handle the unsaturated zone. But we use these techniques, and we use them in cover design. We use them on virtually every problem, whether it's involving slope stability and shear strength or volume change. These two tests will allow us to get the information we need for estimation procedures. The estimation procedures can commonly be used to obtain unsaturated soil property functions for geotechnical engineering applications. This has been my job since, well, over a decade since I retired from the university. The estimations of the unsaturated soil property functions can be significantly improved by combining the results of a drying, gravimetric water content, soil water characteristic curve, and a shrinkage curve. Hysteresis effects may require that specific assumptions be made for each particular geotechnical engineering problem. We would like to be able to follow a drying curve, follow a scanning curve, and go on the wetting curve. There's research done on it. There's some codes that can do it, but it is not necessarily necessary for all cases. I take note that a lot of the cover design work only works with the consultants only use the drying curve. Sometimes they take the drying and the wetting, and they take the average of the two. So I'm talking not in terms of what we can do by way of research, but what we can do to put unsaturated soil mechanics into routine geotechnical engineering practice. I conclude by saying that geotechnical engineers need to develop equipment for testing the soil and analytical protocols that best meet the needs of their profession. We can glean a lot from soil physics, but we can't just take everything out of soil physics and bring it into geotechnical engineering. We have a lot to learn from them, but we have to ask ourselves, where is it important that we make modifications to what they have done? Thank you very much.